Hello everyone, welcome to my channel One Concept Double. This is one of the DC machine question. The main concept in this DC machine question is series field winding turns, series field winding ampere turns, series field winding ampere turns means reduction or increase in series field winding ampere turns. Let's get into the question. Here it is a given is a compound generator with a terminal voltage of 250 volts and has armature resistance, series field resistance, shunt field resistance. Like armature resistance of 0.4 ohm, series field resistance of 0.2 ohm, and shunt field resistance of 125 ohm. If generator supplies 10 kilowatt output power at a rated terminal voltage, what will the EMF generated when it is connected short shunt connection and long shunt connection? Short shunt connection, long shunt connection. Along with the given 1 volt per brush drop. They are asking to find percentage reduction in series field winding turns if an diverter of 0.3 ohm is connected in parallel to series field winding. Means let's suppose this is a series field winding. They are adding some diverter resistance. We need to find percentage decrease or increase in series field winding turns. Let's write down the data here. Given it is a compound generator, its terminal voltage of 250 volts and output power of 10 kilowatt, armature resistance of zero point 0.4 ohm, series field resistance of zero point 0.2 ohm, and shunt resistance of 125 ohm. Now we go for long shunt connection. This is a basic long shunt diagram. Along with I am represented the respective resistance and current notations here. Here the shunt field current is ISH equal to VT by RSH. ISH equal to means shunt field current equal to 2 amps. Output power is 10 kilowatt. Output power is VT into IL. By this I can able to find IL. IL equal to 10,000 by VT. VT is 250 volts. Then the load current is 40 amps. By simple KCL here, IA equal to IL plus ISH. Here the armature current is 42 amps. Now the generated EMF in this long shunt connection is E equal to VT plus IARA plus IARC plus VB. VB is impulse drop. This is series field resistance drop. This is armature resistance drop. This is terminal voltage. By substituting the above values, we get an induced EMF of 277.2 volts. Now they asking what is the reduction in series field winding turns if a diverter resistance of zero point 0.3 ohm is connected in parallel to series field winding? This is series field winding. We add an diverter resistance of zero point 0.3 ohm. Here, in long shunt connection, the series field current will be armature current. Now, by placing a diverter, some current will flow through this diverter. The remaining current will flow through the series field resistance. We need to find the current through series field winding resistance. By simple current division rule, the current through series field winding I equal to IA into RD by RD plus RSC. RD is a diverter resistance, RSC is series field winding resistance. By this 25.2 amps current flows through series field winding. Here ampere turns is number of turns into current. After the modification, the ampere turns is NSC into I. Here I is 25.2. Previously, ampere turns is NSC into IA. IA is armature current. By adding by placing the values in this formula, I got there is a percentage reduction of 40%. Means if you place a diverter resistance of 0.3 ohm, there will be a percentage reduction of 40% in series field winding turns. Now you go for shunt connection. In the shunt connection, first we need to find what is the generated EMF. Here the output power is 10 kilowatt, the load current will be 40 amps. Here in the short shunt connection, current through series field winding will be load current, not armature current. Now we need to find armature terminal voltage. Armature terminal voltage is VA. Here by using simple KVL here, VA equal to VT plus IL into RSC. By this armature voltage is 258 volts. After finding armature voltage, we need to find the shunt field current. Shunt field current is ISH equal to VA by RSH. Then the shunt field current is 2.064 amps. By applying simple KCL here, IA equal to IL plus ISH, the armature current will be 42.064 amps. Now we need to do basic KVL. I am doing KVL in this particular loop. Here minus EG is the generated EMF plus IARA, armature resistance drop, ILRSC, series field resistance drop. Here VT is a terminal voltage, VB is a brush voltage. By substituting all the values in short shunt connection, the generated EMF is 276.82 volts. In long shunt connection, the generation is 277.2 volts. It means in short shunt connection, there will be higher induced EMF. Now, in short shunt connection, we are placing some diverter resistance of 0.3 ohm. In the short shunt connection, we already discussed it earlier. The current flowing through the series field winding is load current. After placing diverter resistance, we are assuming some current I is flowing through series field winding. The I is calculated by current division rule. I equal to IL into RD by RD plus RSC. RD is a diverter resistance, RSC is a series field winding resistance. By this, the current flowing through series field winding is 24 amps. Series field winding ampere turns is number of turns into current. In second case, means after adding diverter resistance, series field winding ampere turns is NSC into I. Before means without diverter resistance, the series field winding turns is NSC into IL. We found the percentage reduction formula is NSC into means before number of ampere turns, after ampere turns divided by before ampere turns. By using this formula, I found the percentage reduction in ampere turns is 40%. Means if you add a diverter resistance of 0.3, there will be some reduction of 40% ampere turns. This question is based on diverter resistance. This series field ampere turns per pole if you place a diverter resistance to series field winding. This is very good question. This sort of questions is mainly given in some of the theoretical exams. If you want to solve this sort of question, please subscribe to my channel.